All right, you thought sampling distributions of means was fun. Well, now we get to do it with proportions. I don't think this is any worse, and just by the fact that you've already done sampling distributions of means, this will probably even be better, okay? So again, if we take a sample and look at the average, the mean, that's going to change with every sample we take. It's a random variable. Well, it's the same idea with proportions. Proportions are very useful for categorical data, but they can all be used in all sorts of places. And that's what we're going to look for here. How do proportions change? How do sample proportions, remember sample proportions, we usually designate as p hat. How do sample proportions change as we take repeated samples? And that's what we're going to investigate with this other link. So just like before, I'm going to kind of do a long explanation, and you can think of this as a kind of a worksheet for you to fill in and look for the answers to these. Maybe go back in the video, see the answers, and ask me if you have any questions. But I'm not going to go through this page specifically filling in the answers myself. So let us discover. So in this little example, we're going to roll a die and count how many of them, how many of the results are 1. We're going to roll a die 60 times. Actually, that's not that fun. That sounds tedious. Let's roll 60 dice once. Imagine getting 60 dice. We're rolling them all. And we're counting how many ones did we get. Well, on average, right, there's a 1/6 chance that a die, a 6-sided fair die, will land on a 1. So if we're rolling 60 of them, how many do we expect on average there to be? 10. 10 ones on average. But sometimes we'll get really lucky and get a bunch, and then sometimes we might get unlucky and not get very many. So we roll our dice 60 times. In this case, I generated a sample. I used the simulation. In this case, we only got 4 ones. We expected, right, the proportion to be 1/6 of 60, which would be 10. 1/6 is about 0.16 repeating. But in this, all right, we rolled 60 and we only got 4. Our proportion was 0.06 instead of 0.17. All right. Well, let's do it again. Let's roll 60 dice again. Okay, this one was closer to what we expected, right? Now there are 11 ones with this proportion. So we're recording these proportions on a dot plot. Very similar to what we did in the last one for means, but now we're using a dot plot instead of those little boxes. All right, let's roll 60 dice again. This time there were only 8 ones, a proportion of 0.13. So we drew a dot at 0.13. Again, again, again. This triangle is showing the average of our proportions. So you're seeing how it's similar, the average of our proportions. And where do we kind of expect this proportion to end up going? Well, I should hope that if we keep on doing this experiment 1,000 times, 10,000 times, I would hope that this proportion would end up averaging out to our true proportion. About 1/6 of these dice should show up as ones. As we keep on generating samples, you can see right above me, this is how many dice are coming up as 1. Sample size isn't changing. This is the proportion every time we do it. Look at that average, that black triangle at the bottom of the graph. Getting really close to what we want. What is our distribution looking like? Oh no, it's looking a little familiar. Let's go faster. 10 at a time. 10 at a time, what's happening? 100. Let's get 1,000 more. Oh, 1,000 more. I know what you're suspecting. You know what's going to happen. I think, hopefully, 1,000 more. Gee, Jason, this is kind of looking like a bell curve. This is kind of looking like a normal distribution. For proportions, it works pretty similarly to means. There will be a couple different things on the back end, but this is what's happening. The average of these proportions, pretty darn close. There's some rounding going on here on this website to what we expect, 1/6. We did this experiment 4,358 times so far with 60 dice each. So yes, we used a computer. This would be unrealistic to do that many times. And the average is about that proportion. The standard error, remember, that's the standard deviation of the sampling distribution. This is our sampling distribution. This is where the mean is, and the standard error is about 0.05. So one way that this is different from our last example is our data here is discrete. Right? We're doing it 60 times, and we're counting, right? There's a finite number, a countable number of dice every time, right? There's nothing in between 1/6 and 11/60ths, I believe this is. All right. So we have a little bit different here with these proportions because we're counting. Proportions are for categorical data. And this using a dice is kind of a weird way of thinking of categorical data, but we are counting the number of ones. It's the same way as we could like count how many people support a bill or a measure or a proposition, or count how many people have red hair, or count how many people have beards, right? Categorical data, proportions are often found by counting a certain time something happens. And usually that's categorical data, but we can count the number of times that numerical data can occur as well. Okay, so that's kind of what's happening here. Now let's modify things a little bit. What if we have a small sample size? Because hopefully you should remember from sampling distributions of means that if we only have a sample size that's smaller, then funny things might happen. Oh dear. What if we did a smaller sample size? What if we only did 10? What do you think is going to happen? All right, so we rolled 10 dice now. 2 came out as ones, so the proportion was 20%. Oh, this time only 1, right? Only 1 die popped up as a 1. The proportion is 10%. Again. 10 at a time. What's happening? Well, first off, because our sample size is smaller, right? There's only 10 outcomes here, right? We can only have, well, 11 outcomes. 0, 1, 2, 3. Like, how many ways can we count? If we're throwing 10 dice, how many ones can there be? Well, a number between 0 and 10. So there's only 10 numbers. Our discrete data, because it's discrete, we're counting, there's only 10 possible outcomes, and some of them are really unlikely, right? Rolling 10 ones, that'd be crazy. All right, so that's one change. If we did 1,000 and another 1,000, this doesn't look like a normal distribution. Again, it comes down to sample size, this value of n right here. Okay, this is skewed data. If we change the proportion, it may or may not be less skewed. All right, and that has to do with, you know, whether there's connections everywhere. I don't have time to go into everything as much as I would like to. So if n is 10, that happens. If n is 100, you know, things will look even better. We'll even have better, like more fine data, because there's 101 possibilities now, as opposed to only 11 possibilities in the last example. And it'll look even more like a nice normal distribution here. More and more times we do this experiment, higher the sample size within each experiment, the more closely it'll resemble a normal curve. So, cool stuff. This is sampling distribution for a proportion. The last thing, I just want to make sure that I kind of talked everything. Yep. So I think we have mentioned most of these topics. So let me know if you have questions, or as you're filling them in, if you run into some blanks. But by and large, it's pretty similar to sampling distributions for means, just some small tweaks. We'll talk more about those in the next video.